data structure using C++ revision 2, we had stopped at this stage. Question 6a, illustrate the railroad car rearrangement algorithm by using queues for the following 3-track example. So here the objective of this system is you have a input track, and in the input track you have a freight train, or you have a long train with the bogies which are addressed in a random number. So bogie, this we expect bogie 1 here, but you have bogie 3, then you have bogie 6, or you call it as a rail car. Okay, a small component, or you call it as a bogie of your train. Okay, so these are not in a proper order. This is in random order. The system which we use over here is a holding track, and here we use the concept of queue here. This is an application of queue, which means this random number has to go to the holding track, and it has to be sorted properly such a way that when it comes out, when the freight train comes out of this output track, all the rail cars are arranged in a correct order. Let us take this as an example. So we will assume that this freight train is having n number of rail cars, that is 9 rail cars, okay, in this case, and this is actually the labels given to each of the rail cars. So we are supposed to arrange it in this fashion. So we will be using holding tracks, wherein this labels will be detached if required. If not, it will be passed directly onto the output track. You can pass this rail cars directly onto the output track, provided if it's in a correct order. Suppose if I get rail car 1 here, then I can directly pass on to the output track. Once this is sorted, once you get this way the rail car arranged, then this can go to the corresponding stations, and you can detach this rail cars for some purpose. Okay, so let's see what this system does. So first we have rail card with number 3. 3 cannot be pushed directly onto this output track. We expect 1. So what we do is we have a holding track with 3 as the capacity. We have H1, H2 and H3. Each of these tracks are having capacity 3 in number. Okay, this is having size 3, this is having size 3, and this is also having size 3. Now first 3 comes, so this 3 can go to any of the track. Let's say that it has been pushed onto the track, holding track 1. So in holding track we have 3 space. So first it goes to the front end. It will be front end now. So first element pushed 3 goes to holding track 1. The second element is 6. Since we have space in holding track, first we have to compare whether 6 is greater than 3. If it's greater, then you can place it behind 3, because in the concept of queue, the element which is pushed onto the track will come out first in the queue concept. So 3 should come first, then 6 should come first. Suppose if we had 2 instead of 6, if we had 2, then we cannot place 3 behind we cannot place 2 behind 3, because we expect 2 to come first, not 3. Okay, so remember, 3 goes first, behind that 6 get placed, then 9 gets placed. Now the capacity in the holding track is filled, and still we are expecting 1, but 1 has not yet occurred. So what we do, 2 is actually the next label. So you have here holding track 3, 6 and 9. So first the 2 is compared here, and the front element 3, when you compare that element, or you can assume that 9 is actually the element now. So 2 cannot go behind 9. You cannot place 2 behind 9, because 2 should go first. So holding track 1 you cannot use. So we go to holding track 2. So in holding track 2, 2 goes and it gets its position. Then we have 4. Now again 4 cannot go to holding track 1. The capacity is full, but still it's not possible. So 4 then it will check in holding track, do you have space. So holding track, one element you have, which is 2, which means 4 can be placed behind 2. So you have 4 goes to behind 2, so that is valid. Then again you have 7, 7 can be pushed behind 4, so that is also valid. So you have now in holding track 2 you have the rail cars labeled 247, and in the holding track 1 you have the rail cars labeled 369. Okay, now the next element is 1. So one element you can directly pass, because this is what we were expecting. So you just directly pass it on to the output track. That's your first label. So 1 goes. After that we expect 2. Okay, so you compare. 8 is actually the element, so 8 element cannot be pushed directly, so it has to go to the holding track. So now where this 8 goes, or before that, after you put 1, okay, sorry, after 1 goes, then the next element which should go out of this track is 2. So it will search in the holding track 1 and holding track 2, do you have 2 present. So when you compare h1, the front element is 3, and in h2 the front element is 2. So 2 is lower than 3, and this can be placed. So 2 goes. Once 2 goes, then we again check the holding track 2 and holding track 1 labels. Now you have holding track 1 label as 3 and holding track 2 label as 4. So 3 is lower than 4, so 3 goes. Okay, then again you compare. Now after that you have the front element present in holding track is 6, and in holding track 2 the element is 4. So 4 is lower, 4 goes. So you have 1 2 3 4. After this we are expecting 5 now. So this searches in the holding track 1 and holding track 2, but the elements are 9 here, and over here you have a element 7. So both are not matching, so it will take the next element from the input track, which is 8. So when 8 comes, 8 is not actually the element which we are supposed to pass directly. So 8 goes to holding track 2. Why it goes to holding track 2? Because we have in the holding track 1 we have 9. 9 is actually the last element which should go. So 8 cannot go behind 9. So here in holding track 2, first element is 7. So behind 7, 8 can go. So 8 goes behind 7. So holding track 2 will be used. Then the next element is 5. So 5 can directly go. Okay, so 5 goes. After that, in holding track 1, okay, in holding track 1 you have 6 now, not 9. Okay, but 9 is actually behind 9, you cannot place. That's correct. So after 5, 6 goes. Then you have 6 goes. Then you have 7. 7 was there in holding track 2. 7 goes. Then you have 8 in holding track 2. 8 goes. Then finally in holding track 1 you have 9, last element. So that is also pass. So this way the concept of road car rearrangement works. So you can just go through this explanation. I have written everything, how exactly this works. It's described. So the program will not be asked here. So they will ask you to demonstrate the working of railroad car rearrangement, that is the queue, application of queue. So application of queue, because here we will be using the concept of queue in holding track. The rail cars are managed in, they are based on the queuing system. Okay, 6b, this question, they have asked you to write a function to perform search operation. So here you are supposed to use the modulo division hash function, which means one important algorithm, linear search or linear probing. That's the algorithm used for searching whether you have a key present in the dictionary or not. And the linear search algorithm, what it does is it will also try to, it will avoid collision first of all. Okay, and also it will ensure that you, for your particular key, which is actually the best position in the dictionary. Okay, so that's the concept used here. So this program you have to write. This is your search program. This is actually the method which will be used here. Hash, that is the key, modulo divisor. This is the modulo function, hash function, and this is your algorithm. It is look whether the dictionary is empty or whether the element which you are looking is the key. So if it's either one, true, return J, or else go to the next bucket if it's not there. Okay, this returns. If it's true, then you have a position where that's the best possible position. If not, search for the next position. Is the next position best feasible one for placing your key in the dictionary? That's what happens here. Just go through the linear probing algorithm for searching an element in dictionary. Seventh question, define binary tree and state and prove 4 properties of binary tree. So the binary tree is defined as a collection, finite collection of elements, and it should not be empty. Okay, binary tree is not empty. So this is having root, and it has been partitioned into 2 binary trees, which we call it as a left subtree and right subtree. So you know this probably you people are comfortable with this module, so you can just highlight the 4 properties. Also you just provide the appropriate proof. So I'll not discuss this in detail, this is already addressed. So properties and the definition of binary tree. Give some examples also, some of the binary trees you can address, and all the components like height, the depth, all those things like left subtree, right subtree, element value, all can be addressed, and highlight everything, because this is asked for 8 marks. This example you can take and you can explain all levels, height, depth, order, degree, so on and so forth. 7th B, draw the binary expression trees for the following expression. So this is again asked in this was asked in the question paper, and this is solved. So you are supposed to draw the binary tree for this expression in form tree, or in order expression has to be converted into a binary tree form, and also you have to write its equivalent for this binary tree. Once you develop, write its equivalent prefix and postfix forms, which is addressed here. Okay, and the second example is this a star b plus c slash d, which is of this form. Okay, and this should be star, should be star, not a plus, it should be star. So here it should be star, my mistake, this should be star. Okay, and postfix comes out to be this, so you replace this by star, so you have to interchange correspondingly here again. This is question number 8A. Again, this was asked for 8 marks. So here you are supposed to describe the array-based representation and linked-based representation. In array-based representation, how you convert a binary tree into an array representation. Suppose if you consider this as your binary tree with the element at the node 1, element is A, at the node 3 element is B, and at the node 7 element is C. So then this will be its equivalent representation, A, B and C, and you can figure out that only 3 memories are used and 4 memories are unused. That's because of this condition. So this binary tree is a right skewed tree. Right skewed tree, you find that many of memory locations goes in vain, or they will not be utilized properly. So if the binary tree is a complete binary tree, then you can figure out that almost all the memory while addressing in array representation will be used properly. So this is one more example wherein this is to some extent efficient than this. So this is A, B, C, and D and E. So 2 elements are empty here. So this, due to which you get this structure. So this is your array representation for your binary tree. Second representation for your binary tree is the linked representation, and it's bit appropriate to represent always for a binary tree. And in this case you have a node, and this node is having 3 components named data, or you call it as an element, left child and right child. So left child and right child are the pointers, and data will be the element present in this node. Okay, so node will be having 3 components, and this left child and right child will be having a data type as a pointer, there will be a pointer pointing to a binary tree node. So this can point to any other binary tree node pointers. All are binary tree node pointers. Okay, so you have to explain this, the node structure for a linked binary tree, and nodes, array representation and linked representation for your binary tree. And this is the program for addressing to find the height of a binary tree. So this program is already explained way back. You can just go to module 4, last slide, you have this program explained. You can just go through it. So altogether again this is asked for 8 marks. Again 8B question. Mention 4 common ways to traverse a binary tree. Implement C++ functions for each traversal method. So 4 common ways to traverse a binary tree are in order, pre-order, post-order and level order. So each of this traversal order method, suppose if a binary tree is given, so what will be its equivalent expression is also addressed. So you can take one simple binary tree, write its equivalent in order, pre-order, post-order and level order expressions. That would do. Then just write the programs, small program, 3 line of code with a condition for pre-order and post-order and level order. Level order, it's bit lengthy, but question was asked. So again this was asked for 8 marks, so concentrate. This is very important, very much. Definitely in almost all question papers I found this question. Traversal method, explain, and also C++ program for all 4 traversal methods. Define priority queue. Explain max heapification with suitable examples. So here you have to address the difference between priority queue and what is a queue. So priority queue, in priority queue, each element present in a queue will be having a priority. Based on this priority you can delete or either you can insert element onto the queue. Okay, so some of the operations for priority queue are find, insert, delete, and to implement this priority queue we use always max priority tree. So in max priority tree we know it should be a max tree. In case of max tree, it should be all the element present at the node should have values higher than that of its children. Yeah, fine. And these are heapification process. So we have to write what is heapification. So how the algorithm heapification works, I've written here how the search for node is accomplished. So first you need to go to the node I is equal to n by 2, and you have to decrement till you get the first node, and you have to compare the parent with its children. So if required exchanging, you have to do it. If not, no need to do it. For example, in this case element 10 you have and 1 you have, so you can figure out that the child is having a value lower than that of its parent, so no need to exchange. If at all, if it's a reverse case, then you have to exchange. Okay, so this explanation with the explanation I've given basically how it works. 9th B, define binary search tree, explain search, insert and delete operation. So here no need to write the program, just explain how do you search element or key element in a binary search tree, inserting and deleting a element in a binary search tree. That has to be explained. So we have written the definition of a binary search tree. This is an example, and to search small explanation is given. How do you search? So just indicate one binary search tree you can take, and with respect to that you can address this always. And to insert, the method I have explained. To delete, I have given an explanation. And one example of a binary tree is considered here, and this was a case wherein you are supposed to delete an element which is not having any child. P is a leaf. For that, one explanation is given. So in the same way, you can consider any binary tree, and you can also explain the search and insert operation. So take one simple example, don't go with the complicated one. So since you've been asked to explain the method, no need to write the program. Kind of algorithm you can put here. 10th one, insertion and deletion process on a max heap. So what I've done is I've just written the program I have pasted, but you have to take an example. You take any example of a heap ensure that it is a max heap, and talk about when you are supposed to insert a new element onto the max heap, so how the structure of the max heap changes, how it gets modified. It should be complete binary tree. All those you can highlight and explain, illustrate with an example. Again, for deleting, the same concept here. How do you delete an element from a max heap? So for deleting direct one, that there is a way. If it's a root element, definitely the root element will be deleted here, which will be the maximum which will have a value, maximum value. So after that, which will be the best position in the left subtree and right subtree, you will look for which one has to be replaced by that you need to look for. Okay. Again, it has to, you have to ensure that becomes a complete binary tree. This is a ADT of binary search tree. So binary search tree is having methods find, insert, erase, and ascend. So this is one new function added, ascend function. So this ensures that all key elements are outputted in ascending order. Okay, so key and pair will be, or key and value will be the data given to the binary search tree, and this ascend function is going to output all pairs according to the key, and it will be sorted according to ascending order. And this also you have to talk about method search for a pair, to search for a pair present in a key. So this is a C++ program you have to address. So program is addressed, final program. So this completes your question paper, June and December 2018, January 2019.